So hi everyone, welcome to the Casper stand up. Uh, um, you know, it hasn't been too active of a week for me because I've been traveling and in Bermuda. But I think there will still be some updates. Um, I guess I'm just gonna like ask Carl to go first. Um,
Sounds good. Um, should I go?
yeah, please do.
Oh,
I find that your updates are
Okay,
normally
so
shorter. I think it's good to get them out of the way. Get out of the way.
okay. Do you hear me?
Yeah, we hear you just fine.
Okay, great. So my update, super short. Been in Bermuda, but when I got back, I began working on a uh, edge case for the fork choice rule, which was didn't quite have the proper behavior, and added that in, and now going to just basically submit it and move forward with the Casper implementation. So not too much.
Want to be a little more specific about what happened in the four choice rule?
Sure. So the if you are so if you have a longest chain and there is a fork that is currently not the heaviest, if you get a commit on a parent checkpoint, which is a descendant of their share, right? But that is not the head of that fork, then what was happening is that the fork choice rule would switch to the fork, but it wouldn't switch to the longest known block, right? It would only switch to like the checkpoint that received the commit. And
I,
so
there's too many words. I didn't. It was hard. Do you have like a picture, or you want to like screen share and draw, or maybe just try again? Somehow I like lost. I lost all the references to parents and common checkpoints and stuff.
Sure, I have to go on my computer to draw, but I'll try to say it really concisely. Okay,
Okay.
so you have two forks, right?
Mhm.
They have a shared root, right?
Mm-hmm.
Now our current head is on fork A, and we receive a commit on fork B. However, the commit is not on the head checkpoint of fork B. It is on one of the parent checkpoints of fork B. So,
Sorry, but it's still above the root, right?
but it's still above the root, exactly. So what would happen is the fork choice would then choose a block that was not the longest the kind of longest known chain for fork B, right? It would instead choose
I
that
understand.
the parent block
The parent block of what?
of fork B,
Meaning the first block at the fork.
the one that received the commit.
Okay. And it wouldn't choose the longest fork.
Yeah,
Okay, so that's just a bummer.
exactly.
Okay. Okay, cool. I thought maybe there was a logic error or something, or like a little more, a
A
little
design error. Yeah.
another one, or maybe what I was usually thinking is maybe you had like a commits on like a second epoch on fork A, and then like you get a commit on fork B at the first epoch, and then would like switch to B or something like that.
Yeah.
That definitely doesn't happen. Yeah.
Yeah, it doesn't.
Cool. Great. Um, Greg, do you want to give your update?
Yeah. I mean, just this week, I discovered we had a typo in our one of our papers. I got some good feedback from a reviewer, but they didn't see that it was a typo. So that was a little frustrating. Anyway, I fixed the typo, and I've just been going through the paper to make sure that um, there weren't any like downstream consequences from the typo. Um, it was just when we were translating the Yoshida combinators into the reflective versions of those combinators, uh, forgot to put an at sign in front of the process that's on the Yoshida side. Um, so anyway, I went and fixed that, and then was double checking all of the downstream consequences. I'll just do a quick screen share so that people can visualize what I'm talking about here. Hang on a second. There's the Zoom thing. So the big difference between the reflective versions of the Yoshida combinators and the Yoshida combinators is this. So there are three differences. This, you send processes, you don't send names. And over here we have the dereference of a process, and then the fact that names are quoted processes. And you can see that. Let's see here. So here, Yoshida only ever sends names. So M is the message combinator for those people who don't follow this stuff closely. Just so that you're aware. So a process is either the null process, the stopped process, or a process that just sends a message to fire and forget. This is a duplicator, so it gets something on A and forwards it out to B and C. This just kills the message. And this is a forwarder from A to B, and then there's a branching left and branching right, and then there's a synchronizer, so you don't get to go and do B and C until after you've done A. So that's the basic setup that she's done, and then the thing that is our work that differentiates our work from hers is that in order for her to build the rest of the PyCalculus, she has to have a new. And she has to have reflection. Replication, not reflection. And for us, we do it slightly differently. So note that you can now send processes, so it's higher order. And here you can take the code, a name, which is the code of a process, and start running it. So there's no replication. And this is how you do your recursion, and here's how you do your branching. And so that's what makes this Turing complete. And then in the translation down here, I had screwed up and put on the Yoshida side P instead of at P. And so I had to fix that and make sure that everything does the right thing. So in particular, the whole thing hinges on when you do the translation, what do you treat the names of the Yoshida combinators as? And what I say is that there are three. I outline at least three different alternatives, but to really hammer home the point that the Yoshida's combinator calculus is completely independent of the names that you use to build the calculus. I just pick, for technical convenience, I pick the names to be the names of the row combinator calculus. So that means that it's perfectly legal to put a row name right here. And then because it's one of those, then you can do this. And then because of that, when you do the translations of the the branch left and branch right, it all works out, right? Because you've got a P here, and so you get the name of P over in the forwarding, which is the only time that one, and then the same with the branch left. You've got a P here, and so you get the name of P here, and those are the two cases that are are of interest. So I was just tracking that down and making sure it all worked properly. So that's my major update. And the reason in the Casper setup, the reason this is important is a few chains, a few steps. We want to be able to apply the ladle algorithm in certain points in Casper, and so we want the ladle algorithm to work nicely in settings where we don't have binders. I'm sorry, where we do have binders, and so we want to be able to show that we can usefully get rid of the binders. And this technology is a way of getting rid of the binders. So, long-winded update, but hopefully it makes sense.
So who did you get to review your paper? I'm just wondering how how you found them.
Oh yeah, no, we submitted to
Okay.
Express SMS. And so we got a really it's the first time in a long time that I was really grateful for conference review. The reviewer really did a good job of reading the paper and understanding, and I was really super grateful they caught this this typo. Unfortunately, it was a typo. It wasn't like a major problem, and we got accepts from the other reviewers, but this reviewer, because of the typo, rejected it. So I'm grateful for the feedback, so I could go fix the typo, but it was a typo and not a thinko, right? So
Oh my god, that's fun.
so we got rejected because of that, but I'm super grateful that we corrected it, and there was no serious issue here. Yeah.
Yeah, that's cool.
Yeah. But the reviewer said really nice things. I'll just use the pronoun she because everybody else uses he. So she implored us to fix it, and she said this is really important work. So that we should fix it and resubmit it somewhere. So that's what I was doing.
That's awesome.
Yeah, I'm excited. I love this kind of stuff. This is really good stuff.
Cool. That's cool.
What about you?
Well, I mean, I don't really have that many Casper updates directly. I do have I guess a couple of updates that are somewhat research related. One of them is I did a bunch of research and reading into kind of transaction costs and the theory of the firm and other theories of the firm that aren't to do with transaction costs and the costs of uncertainty and kind of things that are kind of more like broad economic thinking about what is about basically like the kinds of costs that will be reduced by smart contracts. And it was kind of interesting. One of the more interesting things to me about that was that I was kind of previously underestimating the kind of frictions that exist inside firms rather than between firms. A neat analogy that I came across was that a firm is kind of like a family, and there is not really any the theory of frictions in families is kind of like an interesting and difficult and it's a very different type of theory as like a theory of like transaction costs in a market, because it's kind of much more soft in some ways, right? Because it ends up being
because you don't actually have a market you can touch on and say.
Well, and because you don't have like this kind of institutionalized interface and not with anonymous counterparties, instead it's kind of like
more squishy. Things happen on board meetings and yeah.
You really don't like the way that guy scratches his nose, and and there's like all sorts of weird stuff that could happen, right?
Oh yeah. Been there, done that.
and so that was kind of interesting. Another thing that's interesting is I got a paper from Everett, who works on K framework, about basically rewrite proofs. for general rewrite systems. I haven't made too much progress, but I mean, I still very much get the idea that it's possible to have basically rewrite proofs for and to tell whether two rewrites are in contention, and for the rewrite proof, and for the rewrite, or just from looking at the rewrite proof and the rewrite proofs to be kind of all of the information required as far as like the memoization of that rewrite is concerned.
Yeah, the thing there is that I mean, you can detect up front that there will be conflicts. You can't necessarily detect without a long chain of computation that you're at a particular conflict point.
Right, that's interesting. So that's kind of just a little bit of continuing down the route of making sure that I can specify this data structure that I'm using to do concurrent replication with like one of these correct packet construction consensus protocols that verify that I can actually get the data structure that I need out of a rewrite system. And I'm pretty confident that I can. And basically that's kind of like after I get the safety oracle for the blockchain, and maybe publish the code and stuff. That'll be like one of the next things to do.
The thing that you,
I think it's going to be super interesting to look at concurrent replication as opposed to sequential replication.
Yeah, well, that's what I've been suggesting.
Yeah, well, I mean, it's not.
But the thing,
you have to figure out how to do the sequential one first.
It's not just concurrency. Is concurrency as fits into a lot of other things that we know about the theory of programming semantics. So, I mean, you can shoehorn concurrency into lots of computational models. That doesn't mean that it's a good fit. And it doesn't mean that you have understood, like, how do I explain this? There needs to be a really, really close fit between the way the types work and your notion of when two programs are substitutable for one another in a computational context.
So I'm not trying. So at the moment, I'm not trying to say too much about the computational context, or what will be useful for developers or for smart contracts. I just want to know that if I have like a concurrent transaction model or concurrent smart contract execution model, that I'm able to take advantage of that concurrency, and I want to kind of see, I kind of want to kind of say like, okay, here's the minimum interface that I need for my consensus protocol to take advantage of this concurrency.
Yeah, right.
And then there's like all these problems that you mentioned that like need to be solved kind of from my perspective, like on the other end, on the end of from the point of view, like for the systems for transactioning and smart contracts.
So I would be super
interesting. But basically, like my hope and dream and expectation is that no matter what we come up with there, I'm going to be able to boil it down to the same interface for the consensus protocol.
Cool. So my and I think I'm not the only one that's made this claim, so I would be remiss if I didn't point this out. Probably the smallest APIs or interfaces are presented in the family of mobile process calculi. That's kind of their raison d'etre.
Yeah, so I totally believe that. I mean, I've never seen such a simple current. I mean, so like the pi calculus is like the simplest one I've ever seen.
Yeah, exactly. And so yeah, or I mean, something along those lines. Any
other mobile process calculus that matches the pi calculus in terms of the simplicity of the kind of rewrite system?
Yeah, the row calculus is far simpler.
Oh, okay. Yeah, you're right. My bad. Sorry.
No, it's okay. It's totally okay. Not very many people know about the row calculus. So.
Yeah. Okay, cool. Yeah. So that's cool. So here's kind of a question, I guess. You know, how confident are you that you're going to be able to get like a, really developer friendly high level language that comes down to the row calculus through like a step of like, a sequence of these like correct reconstruction steps?
Well, we have one, and it's already we're already writing token contracts in them. It's called Rolang.
I know. I did look at Roland, but somehow it's not high level enough for me for me to really like. Okay.
What does it mean to be not high level enough? I mean, the total number of lines of code in
the syntax exactly. I guess what I'm looking for is syntax exactly equal to Python.
Well, that we're super close to that, actually.
Oh, cool.
Like really, really close. And that was kind of the whole point, is that you can kind of read a Solidity contract for tokens and then read the Roland contract for tokens, and it should be and just like the average programmer should be able to work it out.
Do you want to do a quick screen share of the code for the token contract?
Yeah, sure.
I want to just like ask a couple questions.
Absolutely. Just a second. So we are at Rolang and examples and regular and token. All right. I haven't looked over this contract in like 20 days, so but here we go.
No worries. I'm not going to ask questions that are that specific.
Okay. All right. So here you go. Let me zoom in a bit. Is that big enough?
Yeah, that looks great. So here's my question. When you call transfer, so say I have like a transaction that calls transfer, that will be associated, I'm pretty sure, with a relatively large number of reductions.
Oh no.
You're telling me there's only one COM event that happens when I call transfer.
Well, we can see what the COM events are. That's the nice thing about the language.
Right. So what I'm saying is there's more than one.
Well, I mean, you can just look right here. So here's one COM event that has to happen in order to reduce.
Yeah. So basically,
and there's the other COM event that has, so that we have two COM events.
Okay. What about the other stuff? Like Xbang, that sends a message, right?
Again, but these are sending messages here.
Sure.
Right?
That's where
that's all. This is the COM event right here.
So there's like two COM events at least. It's basically, so
here's one. So there's some external party that's going to send something to the balances channel, right? Which is going to basically load up the balances on the contract, and then here we're essentially accessing balances as a part of this computation here. So that's pretty much it. And these two things.
So let me rephrase. I'm trying to ask a specific question, and
go for it.
Even if there's only two COM events here for a function call for one of your contracts in your high level language, there might be n COM events. For a single function call, there might be n COM events.
No, typically for a single function call, it's one COM event.
No. So I'm going to I'm not asking typically. I'm asking if there might be sometimes more than one COM event. Or let
me just make sure I'm understanding your question. So is your question like this?
Let me rephrase again, right? What I want to know is whether you're still in a model where you have one reduction, literally like one step in the underlying row of VM for every transaction, or whether you have more than one.
Well, function calls and transactions are distinct. So I'm trying to.
Transactions can call functions.
transactions can call functions, but there's a difference between function calls and transactions.
Yeah, of course.
Okay, cool. Right. So yes, but most of the COM events are actually they're compiled away in many cases. So in particular, in this case here, this really comes down to an assignment. So the compiler says, I don't need to run the COM event. I can just turn this into a single linear assignment. And
Sure,
in this case here, the compiler can see there is no contention whatsoever inside this scope.
Sure. So that's all cool. I mean, I'm trying to get at something like kind of very relatively very basic, I think.
Yeah. So
I don't want to get into
so the transactions that end up on the blockchain, yeah, they're. Hang on 1 second. So damn No, I'm sorry, I can't. We can't have the. If you want headphones or something, you can headphones, but we can't have that on right. Sorry. Okay, so the transactional semantics that we're guaranteeing is that the COM events are the only transactions that show up on the blockchain that we have to worry about.
Okay.
But not all COM events that are in Rolang actually turn into COM events.
But as a user, like I will make a transaction that my client then compiles into lots of different transactions, each of which correspond to one COM event. And what about
we have to make a decision about what we have to make
not also another reduction.
We have to make a decision about what constitutes a transaction.
Well, in Rolang. So what I'm trying to get at is whether or not the decision that you've made can have a transaction that involves more than one reduction.
So just so we're clear, the set of how do I say this? Only COM events correspond to transactions, and there are fewer COM events in the actual execution than what you see in your code.
Sure, I understand that. What I want to know is whether for one transaction there can be more than one COM event.
There can always be lots of COM events. Yeah, you write your code
for a single transaction.
What's that?
For a single transaction.
Again, for a single transaction. So it depends on how you think about joins. So in particular, what I've got highlighted right here is a join. So so you can see that this X here corresponds to this X here, and this Y here corresponds to this Y here. So for this to go, you consume both the X and the Y, and that's atomic.
Sure. Okay. That's fine.
So if you call that, like in terms of the semantics in the row calculus,
it's more than one reduction.
You can think of it as more than one unless you write down the calculus as if it has joins, and in which case it's exactly one.
Okay, great. So I'm happy to assume for now that you're going to have transactions that lead to more than one reduction per transaction, which is to say more than one step in the virtual machine.
What do you mean by transaction? For us, the notion.
So I mean, like a user, so the model for blockchains is like users make these things called transactions, and they change the state of the consensus.
Right, but hang on, but wait a second. But user-defined semantics is not what you have in the EVM. The EVM has a specific notion of transaction, and so from that point of view, user-defined semantics have lots of transactions per user-defined action.
Sure. But I'm not necessarily talking about that at all. I'm just talking about whether or not a single transaction, as far as the EVM is concerned, will lead to more than one step of the EVM's execution. And the answer is like yes. You know, like a transaction can lead to more than one reduction, which is like why we meter and why we have to deal with a lot of stuff.
Okay, but you haven't defined what a transaction is. What is a transaction?
What I want, I'm trying to avoid doing that, right? All I want to say is that a transaction involves more than one reduction. That's all I need. All I want to say is that. Or may involve more than one reduction.
Hang on. I mean, because in Rolang, what we've said is a transaction is a COM event.
And so this is exactly what I'm struggling with and against.
But by that we have
I want to be able to have a set. I want to be able to have a set of COM events, not just one.
You can have sets of COM events. You can have computations.
And they all get and I want them to be like atomically executed, right? I want like all of these COMs or none of them to be executed. So like imagine a transaction is a set of COM events which either all go through or none of them go through. Like is that something like that?
So we absolutely have that. We absolutely have that. Yeah.
Okay, great. So if you have that, then my follow-up question is, can you as efficiently or how efficiently or how precisely can you detect the contention between transactions? I imagine it just falls out of the detection of transactions of COM events. Sorry,
that's exactly right.
I want to hear precisely kind of how that happens.
Right. So you can see it right here. If I have anything else sending on X, I've got contention. If I have anything else sending on Y, I've got contention. Likewise, if I have anything else listening on X, I have contention. Or if I have anything else listening on Y, I have contention. And those are the only possible.
That makes a lot of sense. So that makes a lot of sense and I totally see that for the first level of comms.
For any level.
So tell me about that. So imagine if I have
a nested set of transactions,
and then have a transaction that spends like that intermediate COM, but this first transaction continues to spend more.
So if you have a set of COM events, or sorry, communications. So here's an example. Here's a set of sends and a set of receives, which we write in a single par statement. Now you could have a more complicated par statement, but it will look like this.
I need a certain amount of nesting, I believe, because basically I might be doing COM on a channel that is only set up due to some other COM that happens, right?
So in that particular case, so if you have nesting, then you've crossed a transactional boundary.
Okay, so I'm not sure that I like that. I would prefer to basically have a transaction that says, look, this COM, then that COM, then this COM, and then that third COM maybe could only happen if the first two COMs are successful.
So again, I understand that you have a particular preference, but in terms of the math, this and what we mean by the notion of transaction, right? So they either all go or they don't. Right. So in that particular case, this is the natural transactional boundary.
Well, now, it's the simplest one.
You want to have some notion of, if you want to be able to have some notion of a transactional thing that doesn't get recorded to the blockchain, then you can certainly, and that's the difference between defs versus contracts, right? So you can certainly have nesting inside. You can have multi-level nesting of transactions, but it's really only the entire outcome of this method call that the state of which gets stored. So we can do that.
So that's interesting. Okay, so that's interesting. So you're basically saying like, if there is this third COM that happens as a result of the first two, somehow it needs to be kind of in the def as a consequence rather than in the transaction with the way that you've drawn transaction boundaries at the moment.
That's correct. That's right. And
Okay.
and I think that's
And
the thing that you want.
you think that you would lose any ability to efficiently do contention checking if you extended the transaction boundary to say first do these, then do those, then do those in a kind of
No. I mean, it's the same basic mechanism. All you do is you algorithmically extend that. Of course, the only issue there is that if you have that inside of looping and with if checks, then you have an issue as to whether or not you can know for certain that you'll get there. You'll only be able to say you may get there. Right, but you can you can say with certainty that you may get there. You just can't say that whether you will get there.
Right. So here's kind of what I'm trying to do. Right. I'm trying to look at like take a reduction system and define a transaction for it, and then say, look, okay, if I have a reduction system with certain concurrency, I can define something called like a transaction semantic or something like that in your system. And it's also going to have a certain concurrency profile, and I want to be able to for it to be kind of like naturally and efficiently derivable from concurrency of the underlying reduction system.
So I think I understand what you're saying, and if you separate the boundary of transaction from the reduction in this reduction system, then I mean, there's only going to be so many ways that you can do that that's going to be coherent.
What do you mean by coherent?
In the sense that you won't be able to enforce the good transaction semantics. So in particular, I mean, this has been an active area of research for quite some time, right? So people have, beginning with Elliott Moss, right? People have looked at nested transaction semantics. And in fact, this is one of the threads that led to the mobile process calculi as well, was, nested transactions with, the sort of Elliott Moss style nested transactions don't do everything you want. And so then people started looking at what are called relaxed transaction semantics, where you relax one of the acid conditions. Typically what you do is you relax isolation. So there are some states in which the children transactions can see can see the effects of each other transaction, but then there's some question about whether they all go at once or some of them can still go or something like that. So those are the so you have to define rules.
So that sounds like exactly what I'm trying to drive at, where I'm trying to go with this. And I would love to if you could like help me understand that or link me to stuff, basically, because I think that the reduction system replication is super useful as a conceptual tool. However, I think in practice we're going to want transactions that involve more than one reduction, which leads me to want to replicate a transaction system on top of a concurrent system, a concurrent rewrite system, as opposed to replicate the concurrent rewrite system directly.
Yeah, I mean, I sort of hear what you're saying. I think what you're really going to be looking for is a notion of an observational boundary and when that observation has to be recorded versus when the observation doesn't have to be recorded. So that's the
I think that's true, but also it's not just about observation, but also about so I guess it's kind of a kind of very interactive observation. You observe the effects of an interaction.
Right, and that's exactly what I've got highlighted is all about. So
right, what
comprehension
sounds like what you have is like an observation of interactions that are basically sets of common events. I'm not sure that that's the only or best or transaction model, like sets of common events. I think that maybe we want like this slightly deeper structure of like, okay, first we do this set, and then there's an erase condition, and we like choose that one, right?
Well, we again, we can see. I think what we're discovering, both in terms of empirical evidence as well as from the math, is that if you cut it the way we've cut it, then we have exactly the right level of expressiveness, right? This is on par with the token contract from Solidity.
I don't have any. I guess I'm not worried about expressiveness of the contract language as much as I am expressiveness of the transactioning. Like what So imagine I'm looking at your VM and I want to know, what are all the ways that I can atomically interact with it.
Right, and so since we have I guess what I've been trying to say is we have a very crisp, clear notion of what constitutes a transaction, and by making the choice that we made, we end up with a language that has sort of the right level application semantics as well. So our semantics is based upon the programming language semantics. So we want our transactions to line up with by simulation, and we want that so that we can use types to be able to reason about transactional semantics. So that's kind of crucial.
So that, right? but that seems like you seem to do that with a whole host of different boundaries.
And then what we have to be able to do is to see if that math-driven desideratum lines up with the programmer-driven desideratum. In other words, is the language expressive enough that we can write reasonable application semantics for transactions? And what we're seeing is that, yes, indeed, that does work out. So
yeah, sure, I believe that.
Okay, so but then once you've got that, then what other desideratum would you want? You have a crisp, clear definition.
So here's kind of what I want. Right?
Crisp, let me just finish my sentences. You have a crisp, clear definition of transaction semantics, right? That lines up with your operational semantics and lines up with your notion of types. So that's like super, super high bar. Like no one has ever had that bar before, right? And at the same time, it also lines up with a level of expressiveness, so you're not writing, either programs that are so wordy, so large that it's hard to see the forest for the trees, nor are you writing programs that are so terse that you're getting leader election in one line, right? It seems to be in that sweet spot where it kind of lines up with what programmers are writing. So to the best of my knowledge, no one has ever produced a language of that level of quality before. But if you have another desideratum, now I would love to hear about it.
Sure. So basically, like the way that I'm kind of thinking about it is like there's the virtual machine, the language, and the transaction model they kind of fit together in a certain way. And what I want to understand, or what I want to be able to do, is say, okay, here are all the transaction models. Here's like that's a description of all of the transaction models for which I can get concurrent replication given the concurrencies, like basically like the relevant information for the rewrite system. So imagine I know everything I need to know to replicate the rewrite system. I want to know like what is the set of all transaction systems that where I can just inherit the concurrent stuff so that I can replicate the transaction system efficiently based on like kind of the same, basically exactly. I'm expecting pretty much exactly the same consensus protocol, with a different definition for blocks.
Cool.
And so what I'm trying to do, I'm trying to get at, and I'm trying to understand is, for what transaction models do we get nice properties in terms of the detection of isolation of transactions just from the detection of isolation of reductions? So and so I'm not necessarily trying to necessarily disagree with your transaction model. I just want to know what, like, kind of I say see with a set of communications how I could detect contention just if I know contention on communications. But I want to know, like, how do you draw a transaction? What is like a transaction, abstractly, and is it going to from an abstract transaction going to be able to do all this stuff? My hypothesis is like probably not. I'm probably going to need like some structure, some additional facts about the transaction border to actually get the efficient checks that I'm looking for. And so
Understood. So I think.
What I want is like the broadest set of transaction, or the broadest like collection of transaction, or like description of transaction boundaries or transaction models, for which I get to have kind of for free this concurrent replication.
Right. So one of the things that so a line of research that I haven't spoken about much, but probably I was remiss in not explaining this to you, is so back in the late 80s and early 90s, Christine Tomlinson, Maninder Singh, Paul Atty, and myself did a deep dive on the relaxed transaction processing literature. So in particular, most of the people that we knew of were trying to devise little language DSLs, little domain-specific languages for describing relaxed transaction models. In other words, the class of transaction models was characterized by types of programs within these special purpose languages. And that made a ton of sense. So, and it was at that point that we looked at a variety of different language models for expressing transaction models. And that's when we became convinced that the pi calculus was a proper language for expressing transaction models. So that's yes. So that was in fact my whole raison d'etre for looking at the pi calculus in depth, was because it was not as a programming language, but rather that it had the right set of notions for what would constitute a transaction.
Whoa, cool.
So,
I had no idea about any of this. Yeah.
Yeah, exactly. And so there are a number of papers that we published, and there are a number of papers in the field. And that's what led to the decisions that I made about the Rolang choices about what constitute transaction boundaries. But I can send you all the papers and the links. That's not a problem. It goes all the way back to, oh gosh, there was all this work on sagas and nested sagas, and
great.
Essentially what we did was we were able to show, I mean, it's not a big surprising result, right? You show that all the DSLs that everybody comes up with have efficient encodings in the pi calculus, right? And which is, again, it's, why would this be a surprise? The pi calculus is Turing complete, so you can get encodings in any language you want, right? I mean, it's basically just shuffling the bubble in the carpet. But what the pi calculus has that everyone else doesn't have is a clear notion of autonomy in the par. So that helps you quickly identify which of the different transactional parties you've got. Like, you can just, your eyes can see, okay, I've got 1, 2, 3 communicating parties. Awesome. Right? Takes you like exactly 3 lines of code. You can see, oh, I've got 3 communicating parties. So there has to be some kind of transactional semantics around those communications, right? And the transactional semantics can be, oh, well, we don't care if the communication happens, or it has to happen all at once, or you kind of get the feel for this. And then the other point is that you can syntactically detect that anything in these braces here, anything in these braces here has to be related to the observation of these values on X and on Y. And since that happened across a process boundary here, you know that there must be some kind of transactional semantics related to it. So
that sounds really cool. I mean, that sounds really intuitively pleasing to me. But the reason for that is that basically, like, I'm kind of familiar with the pi calculus, the row calculus, and I can see quite easily how I can detect the relevant information from that. I don't necessarily know that it's like somehow ideal, but I would love for that to be the case, because then I wouldn't need to learn as much.
Yeah, exactly. But in order to convince yourself that that's the case, you have to kind of go through the process that we went through, which was, first of all, seeing that there is no one size fits all model. So that's why everyone ended up with language-based descriptions of relaxed transactions, right? There are lots and lots of different variations of relaxed transaction processing models. Once you see that it has to be a language-based approach,
okay,
then
like, you mean reduction basis isn't good enough? You need to go higher level, or reduction is fine?
So by reduction, so let's look at the relationship between reduction and language. So,
okay, great.
The argument that the language design community has had since the mid 80s has been around operational semantics, which is reduction based, versus denotational semantics, which is that each expression in the language corresponds to a mathematical object, right? And that the evaluation of the language expression to the mathematical object somehow should correspond to your reduction semantics. And there have been a number of key critical examples that the various language design, programming language semantics communities have looked at. Essentially, not to put too fine a point on it, the only options that are left standing from the point of view of practicality are the operational semantics, and operational semantics is all based around reduction semantics. The operational semantics is given in terms of a reduction system, which is why people like Gregory Rosu of K-Framework and many others have spent a lot of time formalizing rewrite systems, because it's all about the reduction semantics.
Right.
And the extent to which the denotational semantics program has been successful is, and again, this is fairly harsh, and I would say it more in a nicer way, if I had more time to think it through. But essentially, the extent to which it's been useful is in informing and elaborating the meanings of the reduction semantics. It's been helpful to know that the bar has been that they coincide, but in practice, you use the reduction semantics. Whether you're talking about Chomsky grammars or you're talking about graph rewrite systems, it's all about rewrite systems.
Cool. Yeah. So I usually I think about rewrites. So my kind of intuition was that, like, rewrite tells you how to, like, make steps in a computational system, which and somehow that corresponds to, if you have languages, a kind of a rewrite of terms in that language, right?
That's exactly correct. That's precisely what's going on. That's it in a nutshell. So,
right.
So now
wrong with my intuitive.
Yeah, no, that's exactly right. So then the next step in the argument is, okay, so you got language. You know that you need your notion of language to describe different transaction models, or you need a notion of language to describe different transactions. And now, what are the features of those languages? And that's when you go back to this table that I drew out. It needs to have an explicit model of concurrency. When you're talking about transactions, dude, it's not even interesting if there's no concurrency, right?
Yeah,
you need to have you need to have compositionality. Again, it's not even interesting from a transactional point of view if you don't have nested transactions. So you've got to have the compositional feature. It needs to be complete.
But you also want to be able to continue to check isolation even under composition.
Well, you need to be able to express what are your different isolation characteristics, right? And you may not have.
And like I really would like if I could tell efficiently if two transactions are isolated always.
Yeah, absolutely, exactly. But in terms of the properties that I laid out, these are the ones that are relevant here. So concurrency, compositionality, completeness, it goes without saying. And now comes the interesting bit, which is all and wound up in your use of the word efficiently: complexity, right? So you need to have a model of complexity in the model. And by the way, that doesn't exist for lots and lots of models, right? The lambda calculus sucks at complexity, even though it's a highly successful model of computation. So you have to have all four properties come together in your language, okay? And at this point, we have now eliminated all but the mobile process calculi as the model of computation to represent your language for transactions.
I didn't follow how they all got eliminated. Sorry.
Okay, so that
I believe that the lambda calculus doesn't have it. I don't know why the other.
Okay, so I mean, I can. It's worth going through that table again. I'll go through it, and then next time, just remind me, and I'll do a screen share of the table. Okay, so so the features are concurrency, compositionality, completeness, and complexity. Those are your features. And we've just gone through why you need those features for transaction semantics. So hopefully that part of the argument is accepted. So the other part of the argument is now just to go down the list of the proposed computational models and see which ones have all four features, which is what I did in the late 80s, and noticed, oh, wow, there's a gap here. This is before I found the mobile process calculi and before Milner found the mobile process calculi. And I said, let's see. Well, Turing machines, no explicit model of concurrency, they're out. Lambda calculus, no model of resources, it's out. And, and you just go down the list. Petri nets, no compositionality, it's out. And you can go on and on. Like Turing machines are out on two accounts, right? Because you could potentially have, you can adjust Turing machines so that they have a notion of concurrency, but then they're not compositional. And you can just go down the list. You just go down the list of all the proposed notions of computation. And in the late 80s, there was no mobile process calculus.
I guess what I'm saying is that, I totally believe you that pi calculus has all these properties. And that the row calculus has all of them. I don't know that anything that has them resembles them.
Well, again, the kind of the point is you might go and invent something, or you could just use the things for which we have an extremely well articulated theory.
Okay, yeah, fair enough.
Okay, so the main thing here is just, do you believe that those properties correspond to transactional semantics? If you do, then you're looking for models that have those properties. And there's a family of them, right? There's not just one. There's a whole bunch of them. There's the blue calculus, there's the ambient calculus. There's, you can go, and then you can go and research all of those and figure out which ones of those really have the features wrapped up in the way that you want, right? And once you've done that research, then you can start investigating transactional models. You still there?
Sorry, I was speaking on mute. That sounds really cool. I would love to, understand it as well as you do. And I guess I'm going to work on it. But basically, what I'm trying to do is provide the most like general consensus protocol that does this thing, and I think you'll definitely be able to put the PyCalculus thing on the back end, but I think you might. I think I'm hoping that as many things as possible that I can replicate as many things as possible, right? I want to have like kind of the to give like the minimum natural interface required to replicate a transaction system. And I'm just kind of wondering and hoping that and expecting that I'm not going to have to do that much. It's not going to be that different from the system for replicating rewrite systems.
Yeah. I mean, I think the work that you and Kent and I did before is a kind of natural jumping off point, right? So
exactly, yeah, that's pretty much exactly the work that I'm referring to here. And basically, I as long as I can, and what I'm basically hoping is that for any reduction system, I believe that I can get what I need. I don't believe I can get it from any transaction system, and I want to be able to say, okay, here's a way that like or ideally I would say, okay, as long as your transaction system is a result of applying like this operation or this function or this or is in this family of terms that are derived or some things that are derived from the reductions in this way, then you get to have this stuff for free.
Yeah, so I think what I was trying to suggest is that the notion of replication is going to come with a notion of what state is, right? If it doesn't have a notion of state, then it won't be able to consistently replicate something.
Of course, so yeah, and basically the concurrent schedule will be such that like you get the same state no matter like which order you executed it.
Right. So just to complete the thought. So the notion of replication has a notion of state in it, that it comes, it's its own baggage, right? It says, I know what state is. And then the rewrite system, whatever rewrite system you're attempting to replicate, it also has its own notion of state. And then what I was saying about coherency is that in order for these two ideas to line up, they have to be coherent about what they believe state is. And there are some other things that have to be coherent. And now to motivate why why Mike and I have chosen higher category theory in which to reason about this piece of the puzzle is because higher category theory has kind of the best way to talk about coherency. So essentially coherency between two things comes down to some kind of commuting diagram. And or some notion like that. It's expressed as a kind of commuting diagram, and that's why we've gone to a lot of trouble to express. Just to be clear, it's really hard, and we proved how hard it is to get PyCalculus semantics over into a categorical setting. This is not straightforward at all. But once you pay, so in other words, there's a lot of pipe fitting to match the higher categorical notions of computation to fit with the transactional and concurrency notions of computation. Once you do that pipe fitting, then you can utilize what is a crisp idea of coherency to enforce coherency between the replication system and the rewrite system. And that was the motivation for that piece of work. And in fact, that's at the heart of the whole Casper as trace. Right. So this idea that in fact the categorical notion of trace is what gives you this replication system, is to work out precisely what that notion of coherence is. Does that make sense?
It made a lot of sense until the end. I didn't understand what you meant, what you were referring to by that notion of coherence.
to work out what has to be coherent between the rewrite system and the replication system. So to be able to write down, in other words,
sure. So there needs to be some correspondence between the thing, like a thing that gets replicated, and a particular reduction in a rewrite system.
That's exactly right. And in particular, so just because the category theory can tell you crisply what coherence is in general, it's going to rely on you to say, well, but I'm really talking about this particular set of commuting diagrams. Right, that set somehow crisply characterizes what has to be coherent between these two things. And what I've been arguing is that the notion of trace crisply characterizes exactly the set of commuting diagrams that
cool.
has.
I would love, I can't wait till I understand.
Awesome. Well, that's why we have these stand-ups. I actually